Hello, during this session I'm going to be talking about a special type of star called a Cephied variable. I'm going to explain how we can use Cephied variables to calculate the distance of more distant stars, in fact, even galaxies. So let's start at the very beginning. Mr. John Goodricke was the first person to noted the luminosity of delta Cephied varied regularly, and because the first star was the delta Cephied, so we have what's known as the Cephied variables, the group of which this is the first one. He said, "This night looked at Beta Persei and was much amazed to find its brightness altered. It now appears to be fourth magnitude. I observed it diligently for about an hour upwards, hardly believing it had changed its brightness because I'd never heard of any star varying so quick in its brightness. I thought it might perhaps owing to an optical illusion, a defect in my eyes, or bad air, but the sequel will show that its change is true and it was not mistaken." So that was the earliest discoverer. As time went on, delta Cephieds were studied in more detail, and it is seen that the star delta Cepheid, which obviously became a class of its own, went through a process because of the inner thermonuclear process and the interaction of gravity and radiation pressure caused them to blow up periodically and shrink in defined times, and not only change their size but also their color and surface temperature and brightness, and therefore there's a change in luminosity over a regular sequence. So here's an example over time. We can see the luminosity goes up and down, up and down. Now, these Cepheids can be found on what is known as the strip of instability. So they're stars and they occur coming off the main sequence along this fine strip here. And that's the one place that they exist. Now, they're interesting because what happened was Henrietta Leavitt, one of the truly great female astronomers, studied variable stars that were about the same distances away. So it happens that they were appearing in what's known as the large Magellanic cloud and the small Magellanic cloud. And what was found is that their pulsation periods were related to brightness. So an example of this is our North Star, Polaris, and it's not constant, it's actually a Cepheid variable. Now, knowing that they all have the same distance, what we could do is then look at the relationship between luminosity and period. And what was startling discovery was there was not only that Cepheid variables varied over a regular set of time, it appeared that their luminosity was directly related to their period of changing luminosity. Now, this is really, really useful for a number of different reasons. For a star, it gives us the ability to find out the luminosity of a star just by looking at its change in brightness. Now, this is great news, because what you can do is then you can work out the distances to Cepheids. So the distance to the closest Cepheid, Delta Centauri, in our galaxy can be found using parallax measurements. And then from this statement, we can determine the constant in the relationship between period and luminosity. This isn't needed for the exam, by the way, but as it happens that we'll have an L equals K, which is a constant period to 1.3. Now, this is really great news because Cepheids are very bright stars. They can be seen actually standing out in other galaxies, and they can be picked up to a distance of 10 million light years away with the Hubble Space Telescope. So that means where we had some issues with working out distance with parallax, we can use Cepheids to be able to work out the distance even to other galaxies. And because the period of the Cepheid is related to its absolute brightness, if we observe its period and its apparent brightness, we can then work out the distance of which that Cephied exists and that galaxy exists to within about 10%. So this is a really, really useful. It gives us what's known as a standard candle, something which we can look at and we know what brightness it should be, and therefore from the brightness we observe we can work out the distance. So a Cephied question example. The star delta Cephied is 300 parsecs away from Earth. Another variable star is detected in a distant galaxy that has the same period of delta Cephied, but an apparent brightness of 10 to the minus 9 of delta Cephied. How far away is it from the galaxy? Okay, so we've got lots of information there. We've got the distance of 300 parsecs of delta Cephied, which we know. We know that it has the same period, so therefore we know it must have the same luminosity. So how far away is the galaxy? If the two stars have the same luminosity, that means the luminosity of one star is the same as the luminosity of my delta Cephied. So that means that 4 pi d squared of the star times the brightness of the star is equal to 4 pi d squared of my delta Cephied times the brightness of my delta Cephied, and therefore I can rearrange these things and work out the ratio of distance, which is 3.2 times 10 to the 4, and that's the ratio. If I already know the distance to my delta Cephied, it means that I can do 3.2 times 10 to the 4 times 300 parsecs, which gives me 10 megaparsecs, which is the distance to this Cephied in another galaxy. So that's the type of question we'd expect from about Cephieds.